Continuing with the section 3.1 notes, we now move to example 3. Write the standard form of the equation of the parabola with vertex 4, -1, and which also passes through the point 2, 5. So here we're given some information about a parabola, but we're not given its equation. We want to find the equation. So we're going to make use of the standard form, and I'll begin by writing, just in general form, y equals a x minus h squared plus k. Okay, so what we need basically is a, h, and k, the values of a, h, and k. Well, the vertex is given 4, -1. So h comma k is the vertex. Therefore, it follows that h must be 4 and k must be -1. So we can write our equation now as y equals a x minus 4 squared plus -1 or just -1. So the only thing left to determine is the value of a. And for that purpose, we can use the second point that is given, 2, 5. That is, let's let xy be 2, 5. If 2, 5 is a point on the parabola, it should satisfy the equation of the parabola. So if we substitute x equals 2 and y equals 5 into our standard form equation, we can determine the value of a that would cause that point to satisfy the equation. So with that in mind, let's replace y with 5, x with 2, and solve the equation for a. This would give us 5 equals a -2 squared minus 1. That is 5 equals 4a minus 1. -2 squared is 4. Add 1 to both sides to obtain 6 equals 4a. Divide both sides by 4. A equals 6/4. That is 3/2. Therefore, our equation would be y equals 3/2 x minus 4 squared minus 1. This is going to be your final answer. You want to make sure you write your equation in terms of x and y at the end, with h, k, and a determined as shown previously. Now we turn to the following question. If a quadratic function is not written in standard form, how can we deal with it? How can we determine the vertex? How can we sketch its graph? There are two approaches that can be taken in this situation. One method is to algebraically convert the function or the equation into standard form by using the method of completing the square. Sometimes this method is not too difficult. Other times it can be a little bit tricky. So I'm going to take a second approach and not require you to use completing the square. And the method we're going to use is to just rely on what's called the vertex formula, which is a very simple result and easy to apply. The vertex formula says the following: given the quadratic function f of x equals ax squared plus bx plus c. Notice that is not the standard form. That's more what we might call the general form that we gave at the very beginning of the notes. The vertex xv, yv of its parabola can be found as follows. The x-coordinate of the vertex is minus b over 2a. That is the opposite of b divided by 2 times a. The y-coordinate of the vertex would be the value of the function at the x-coordinate of the vertex. So substitute the x-coordinate back into the function to determine the y-coordinate of the vertex. So essentially, the vertex formula is x equals minus b over 2a. That's really all you have to use. Also, the x-intercepts can be found either by factoring ax squared plus bx plus c, if that's not too difficult to do, or by using the quadratic formula. So you do need to know the quadratic formula in cases where standard form is not given, because you may need to use it, especially if the x-intercepts are not rational numbers, if they involve irrational numbers. So to illustrate the use of the vertex formula, let's look at example 4, which actually takes us back to a previous example we did. Recall the function y equals negative 2 x plus 1 squared plus 6 of example 2b. Write it in the form f of x equals ax squared plus bx plus c, and then find its vertex and intercepts. Now, we already did this problem previously making use of the standard form, which is the form that the equation is already written in. So this function comes in standard form. So the vertex and intercepts can be determined directly from the standard form. And it's not necessary to use the vertex formula in this situation. However, to illustrate the use of the vertex formula and to show that it gives us the same result as what we obtained previously, we're going to rewrite this function in a different form and then use the vertex formula. So the first part of this problem is not something you would generally do, but it will just show how the vertex formula is connected to this previous example. So what I'm going to do is rewrite this function in a different form. So I have y equals negative 2 x plus 1 squared plus 6. And what I'm going to do is I'm going to square the x plus 1 by FOIL. It would be x squared plus 2x plus 1. It would not just be x squared plus 1. It's x plus 1 times x plus 1. So x squared plus 2x plus 1. Then multiply each term by negative 2, except for the 6, since that's not in the parentheses, and then simplify. What that will give me is negative 2x squared minus 4x plus 4. And now I have this equation in this alternate form, and let's suppose then that we were given the equation in that form to begin with, and show how we can obtain the vertex and intercepts directly from this new form. So what we need to do is identify A, B, and C. A is negative 2, B is negative 4, and C is positive 4. Now for the vertex you just need A and B actually. So the x-coordinate of the vertex, xv, by the vertex formula is minus b over 2a. So that means the opposite of b, which is positive 4, over twice the value of a, which is negative 2. That is 4 over negative 4, or negative 1. That's the x-coordinate of the vertex. Now what's the y-coordinate of the vertex? Well, the y-coordinate, y sub v, is found by substituting the x-coordinate back into the function. So that is into this form here that we converted into a moment ago. So we would substitute negative 1 for x, squaring it, subtracting 4 times negative 1, and then adding 4. Negative 1 squared is 1, times negative 2 is negative 2. So we'd have negative 2 plus 4 plus 4 and that gives us positive 6. So the vertex, using the vertex formula, is negative 1, positive 6. If you compare that to the result from example 2b using the standard form, that's the same vertex we obtained before. Next we'll find the intercepts, again working from this more general form. And for the intercept, for the x-intercepts, you want to set y equal to 0. So we're going to be solving the equation 0 equals negative 2x squared minus 4x plus 4. Now, I could divide out 2 or negative 2 to simplify this a bit, but to avoid confusion, because we previously identified a to be negative 2, b to be negative 4, c to be positive 4, I'm going to just leave the numbers as they are. So we're going to use a quadratic formula with a equal to negative 2, b equal to negative 4, c equal to 4 to solve this equation. We could attempt to factor it, but we would find that this polynomial does not factor. So the quadratic formula gives minus b plus or minus square root b squared minus 4ac over 2a. So then substituting in a, b, and c, for b we would write positive 4, it's the opposite of b, plus or minus square root. B squared is negative 4 squared, which is 16, minus 4. A times c is negative 2 times 4, which is negative 8. Take the square root of that whole thing. Divide the whole thing by 2 times a, which is 2 times negative 2, which is negative 4. Now simplify. 4 plus or minus square root 16 plus 32, all divided by negative 4, or 4 plus or minus, so we have 32 plus 16, 48 over negative 4. Now 48 is 16 times 3, so that would be 4 plus or minus 4 times the square root of 3, bringing out the 16, taking its square root, over negative 4. That gives us actually two solutions. X equals 4 plus 4 square root of 3 over negative 4. Dividing by negative 4, that would give us 4 over negative 4 is negative 1. 4 over negative 4 again is negative 1, so minus 1 minus square root of 3. And then the other solution would be x equals 4 minus 4 square root of 3 over negative 4. Dividing by negative 4, we would have 4 over negative 4 is negative 1. Negative 4 over negative 4, positive 1, so plus the square root of 3. So the x-intercepts would be basically negative 1 plus or minus the square root of 3, comma 0. And again, that's what we obtained previously in example 2b. Finally, the y-intercepts can be found rather easily, much more easily than the x-intercepts in this case. If we take our original function, y equals negative 2x squared minus 4x plus 4, and substitute in 0, let x equal 0, we would obtain y equals 0 minus 0 plus 4. We would get 4, and so our y-intercept would be at 0, 4. If you compare all of this to what we did previously, it's exactly the same results, just obtained through a different method. And this is a method we can use even if the standard form is not given originally.